Welcome to the world of operating systems. Today, let's understand page faults. Page faults occur when a program tries to access a memory page that is not available in the main memory. This presentation will help you to understand how operating systems handle these missing pages. So, what exactly is a page fault? A page fault happens when a program tries to access a memory page that isn't currently mapped to the physical memory. Think of it like trying to find a file in your computer's folders, but it's not there. When this happens, the operating system must retrieve the required page from secondary storage, like a hard drive, and load it into physical memory before the program can continue running. In simpler terms, the operating system needs to fetch the missing piece of data from the disk and put it into the main memory so the program can use it. Page faults can be of two types: minor and major page faults. Let's begin with minor page faults. A minor page fault occurs when the page you need is already somewhere in the memory. No need to go to the disk. It's just that the process's page table, which keeps track of where each page is, hasn't mapped to its location yet. Because there is no disk access involved, these are much faster to resolve. Next is major page faults. A major page fault occurs when the page is not available in the memory at all. The operating system has to go to the secondary storage like the hard disk and get it. This is a much slower process. Let's see the step-by-step process that happens behind the scenes when a page fault occurs. The first step is that the central processing unit or CPU attempts to access a page that is not in the physical memory. In the next step, the memory management unit or MMU detects the page fault and triggers an interrupt to alert the operating system. The operating system then saves the current state of the process that caused the fault and transfers control to a special routine called the page fault handler. The operating system locates the required page in secondary storage, such as a hard drive. Next, the operating system loads the page into a free frame in physical memory. Finally, the operating system updates the page table to reflect the new location of the page, restores the process state, and allows the process to continue execution. Now consider a scenario where a page fault occurs and the memory is already full. The operating system must decide which page in the memory to replace with the new page. This is where page replacement algorithms come into play. Some of the popular algorithms are first in, first out, least recently used optimal and clock. Let us start with the first one, which is first in, first out. This algorithm replaces the oldest page in memory, regardless of how frequently it's used. It's simple to implement, but can sometimes lead to something called Belady's anomaly. Let us see the next one. Least recently used or LRU. This algorithm replaces the page that hasn't been used for the longest time. It's generally more effective than FIFO, but requires tracking the access history for each page. Next is optimal. This algorithm replaces the page that will not be used for the longest time in the future. It's the best theoretically, but impossible to implement in practice because it requires knowing the future. The final one is clock, also known as second chance algorithm. This algorithm is a compromise between FIFO and LRU, using a reference bit to give pages a second chance if they've been accessed recently. This is more efficient than FIFO with a lower overhead than LRU. Now let's discuss how often page faults occur and their impact on performance. The page fault rate tells you how frequently page faults happen during program execution. A high page fault rate could indicate what's called thrashing. This is a situation where the system is spending more time handling page faults than actually running the program. The page fault rate is affected by how much physical memory is available, which page replacement algorithm is used, and the program's memory access pattern. The effective access time of memory with paging is calculated using a formula. It depends on the page fault rate and the time it takes to access memory versus handling a page fault. Even a small increase in the page fault rate can significantly slow down program execution. This is because accessing data from main memory is much faster than retrieving it from the disk. Now let's explore techniques to optimize page fault handling. First one is page prefetching. This proactively loads pages into memory before they are requested. The operating system predicts which pages will be needed based on past access patterns and loads them in advance, reducing wait time when those pages are eventually accessed. Next is demand paging. Demand paging loads pages only when they are actually needed, rather than loading the entire process into memory at once. This reduces initial loading time and memory usage, but it might cause more page faults during execution if pages are accessed for the first time. The third one is working set model. This involves tracking the set of pages a process actively uses during a specific time window. By ensuring that a process has its most important pages in memory, it can reduce the frequency of page faults. The final one is thrashing prevention. This involves detecting when the system is spending too much time handling page faults and taking corrective action. Solutions might include reducing the number of active processes or allocating more memory to the affected processes. Here is a quick summary of key points we covered today. Page faults are essential mechanisms in virtual memory systems that handle missing pages. Minor page faults, where the page is already in memory, are much faster to resolve than major page faults, where the page needs to be fetched from the disk. Page replacement algorithms like FIFO, LRU, and clock determine which pages to evict from memory when it is full. The page fault rate significantly impacts system performance, with even small increases causing major slowdowns. Thrashing occurs when a system spends more time handling page faults than executing programs. Optimization techniques like prefetching and the working set model can reduce page fault frequency. In conclusion, efficient page fault handling is crucial for balancing the benefits of virtual memory with the performance costs of accessing secondary storage. Thank you. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.